Today, we are going to explore the concept of pipeline architecture. In the quest for faster computing, simply making the clock tick faster isn't enough. We need to be smarter about how we execute instructions. Pipeline architecture is the fundamental technique used in modern processors to increase throughput by doing more than one thing at a time. Over the next 10 minutes, we will break down exactly how this works, look at the visual mechanics of it, and weigh the significant advantages against the inevitable limitations. To understand pipelining, we first need to understand the lifecycle of a single instruction. The process of executing an instruction in a digital computer is not instantaneous. It involves following 4 major steps or stages. 1. Instruction fetch, getting the order. 2. Instruction decoding, understanding what the order means. 3. Operand fetch, getting the data needed for the order. 4. Execution, actually performing the task. Think of this like a factory assembly line. You can't assemble the car until you have the parts, and you can't get the parts until you know what car you are building. Let's look deeper into what happens at each of these specific phases. First is the instruction fetch phase. Here, the processor reads the next expected instruction from the main memory and sends it for decoding. Next is instruction decoding. This step determines the opcode, what action to take, and the operand specifiers, what data to use. Third is the operand fetch. After decoding, the system fetches each required operand from memory, though it is worth noting that operands already sitting in registers do not need to be fetched. Finally, the execution phase. This performs the indicated operation and stores the result in the specified destination location. This linear process is what happens for every single command your computer processes. Now, here is where the architecture changes the game. In a non-pipelined processor, the next instruction will be fetched only after the complete execution of the previous instruction. It is a strict queue. Instruction 2 waits for instruction 1 to finish completely. In contrast, pipeline processors execute successive instructions in an overlapped fashion. This means new inputs are accepted at one end before the previously accepted inputs even appear as outputs at the other end. So, we can say that pipelining makes use of the idle time of the hardware. While the execution unit is busy with the first job, the fetch unit is already grabbing the second job. All these stages are triggered and synchronized by a common clock. This concept is best understood visually. Please look at the diagram on this slide. Diagram explanation speech. This matrix visualizes the overlapped fashion we just discussed. On the vertical axis, we have the instructions, instruction 0, 1, 2, etc. On the horizontal axis, we have time cycles, 1, 2, 3, 4, etc. Look at instruction 0. In cycle 1, it is in the if, fetch stage. In cycle 2, it moves to ID, decode. Now, look at what happens in cycle 2. While instruction 0 is busy decoding ID, the processor doesn't sit idle. Instead, it starts the if, fetch stage for instruction 1. By cycle 4, the pipeline is full. We have 4 different instructions in 4 different stages simultaneously. Instruction 0 is in execution, EX. Instruction 1 is fetching operands, of. Instruction 2 is decoding, ID. Instruction 3 is fetching, if. This staircase pattern is the visual representation of throughput. Without pipelining, instruction 1 wouldn't even start until cycle 5. Just to ensure we are all on the same page regarding the notation used in that diagram and for the rest of the talk, here are the standard abbreviations. IF stands for instruction fetch. ID stands for instruction decoding. OF stands for operand fetch. EX stands for execution. These are the building blocks of the pipeline. In the context of parallel computing, the advantages are massive. First, we can achieve superlinear speedup in specific cases. By splitting a massive dataset or neural network model across multiple processors or stages, you can fit models into memory that would essentially crash a single processor. This avoids the incredibly expensive process of swapping data to the hard disk. Second, we are hiding communication latency. While one stage computes, another stage can transmit data. A well-tuned pipeline overlaps computation with communication, effectively hiding the time cost of moving data between cores. Third, we get specialized hardware utilization. Different stages can be assigned to different hardware. For example, Stage 1, data preprocessing, can run on a standard CPU, while Stage 2, matrix multiplication, hands off to a GPU. However, pipelining is not magic. It comes with distinct limitations that engineers must manage. The first is the bubble overhead. In parallel model training, the pipeline often has periods where some GPUs or stages sit idle waiting for data to flow down from the previous one. We call these gaps bubbles, and they reduce total hardware efficiency, often keeping it below 100%. Next is the pipeline flush penalty. If the system needs to change direction, say, an error occurs or a branch misprediction happens, we have to flush or delete all the data currently in the pipes. This destroys significant amounts of partially completed work. Finally, there is load balancing difficulty. If Stage A takes 10 milliseconds and Stage B takes 15 milliseconds, Stage A will always be blocked for 5 milliseconds waiting for B to finish. In parallel hardware, this is known as the straggler effect, where the speed of the entire cluster is limited to the speed of the slowest node. In conclusion, pipeline architecture is a critical strategy for maximizing processor efficiency and handling large-scale parallel tasks. By overlapping instructions, we hide latency and utilize hardware better, but we must always be vigilant against bubbles and load imbalances that threaten that efficiency. Thank you for your attention.